Okay students, so here now in this video we are going to see another important theorem called as Schroeder-Bernstein theorem. This one is important only since it's a name theorem. Now what does it says is that let f from x to y be a function and g from y to x be a function, and if f and g are 1 1, then there exists a bijection h from x to y if f and g are increasing also. Okay, so now let's see what does it says. Let's see how to prove this. Now f is from x to y, g is from y to x, and both are 1 1. What I will do is I will consider a function capital F from power set of x to power set of x. Okay, and it is given by, I will define it to be f of some s is equals to capital X minus g of y minus f of capital S. Okay, we'll see this via example or via a diagram. That is what f of s is equals to x minus g of y minus f of s. Okay, so the diagram looks like this is going to be my x set, this one is going to look my y set. Okay, now f is from here to here, g is from here to here. Okay, so now s is a set in x, so my f of s, this part, f of s part lies here. Okay, and this part is my y minus f of s, so y minus f of s is going to be a subset of capital Y. So now G is going to work on that y minus f of s. So now G of y minus f of s is going to lie here. So G of y minus f of s. Let's say it is lying in some this kind of part. Okay. So now what we are interested in is x minus g of y minus f of s. So whatever this part is x minus g of y minus f of s. Okay, or entire this part, and this becomes my f of s basically. Okay, so now this is how diagrammatically it looks like. We'll see, my claim is, or what does this theorem states is that there exists a bijection h from x to y. Okay, so for that what I will do is I will define a function f. I have defined this capital F. What I will do is I will show that this capital F is increasing. Now, increasing in the sense we had seen in the Nestor-Tesky lemma that if A is a subset of B, then f of A is a subset of f of B. This is what a increasing function looks like. Okay. So now what I will do is I will take two subsets of x. I'll say let A be a subset of B and both being the subsets of capital X. Okay. Now what I know is capital F of A is a subset of capital F of B. Why? It is given that F is increasing. Okay, it was given in the theorem that F and G are increasing, small f and small g. Now since this is the case, that means what? Y minus f of b, that is the complement of this, is a subset of y minus f of a. Okay, why? Because I know if a is a subset of b, then b complement is a subset of a complement. This is from the set theory part. Okay, so y minus f of b is basically a f of b complement. Okay, so now since this is the case and my g is also increasing, I can say g of this part is a subset of g of this part. Okay, so what I will do is g of y minus f of b is a subset of g of y minus f of a. Now, why G is increasing? Now, this both of these are going to be a lie in X. Okay, so their complements are also going to be X minus this X. Okay, so again I know by the same that A, if A is a subset of B, then B complement is a subset of A complement. I know X minus G of Y minus F of A is a subset of X minus G of Y minus F of B. Okay. Now from here, if I going to see, it becomes the complement of the complement part. So this basically becomes equal to this function I have defined is capital F of A is a subset of, this becomes the definition of capital F of B. This is how the similarly capital F has been defined. So from here what I know, F is increasing. Okay. Now if F is increasing, I can use the Nestor-Tasky lemma. What does that Nestor-Tasky lemma says? That if from some set x to y you find a function f such that f is increasing, then it has a fixed point, let's say f of s is equals to s. Okay, so in this case I'll take some b, fixed point f of b is equals to b. So what does it say? There exists a b which is a subset of x such that f of b is equals to b. But what is f of b now? F of b is x minus g of y minus small f of b, and this becomes equal to b. Now this implies g of y minus f of b is equal to x minus b. Okay, so now what I will do is this x minus b, I'll name this as set a is equals to x minus b. Okay, b I will name as b itself. D I will name as f of b. Okay, then C I will name as y minus d. That is basically y minus f of b. So if I draw this diagram from x to y, how it will look? X is there, here there is y. So here there is going to be a b. Okay, and x minus b is going to be this part, x minus b, which is equal to a now. Then if b is there, f of b is going to lie here, and f of b is my d, and c is my y minus d, that is this c part. Okay, so a, b, c and d. Okay, so from here to here, x to y there exists f, and from y to x there exists g. So I can say f is from b to d and g is from c to a. Okay, and both becomes onto functions. Obviously both of them become onto functions. Okay, since b to f of b it becomes onto, and from c to x c to a it also becomes onto function. Okay, now already f and g were given to be 1 1 functions in the theorem. That means what? F and g are bijections. So what I can do, we wanted one single bijection for both of them. So what I can do is I can define a combination of both this, that is h from x to y, defined by h of x is equals to f of x if x belongs to b, okay, and g of x or g inverse of x if x belongs to a. Okay, so if G is a bijection, that means G inverse of X is also a bijection. Okay, so therefore hence proved there exists a function. Now next thing is about countable sets. See, any set A is said to be countable if you can construct a bijection f from a to a set of natural numbers. Okay, we know how to construct a bijection. See, from a to in, if you construct a bijection, this a is said to be a finite set. This we had seen already, and we had already seen for checking the cardinality or make checking or verifying whether the cardinalities of two sets are equal or not. What we had done already is we used to take one set x and another set y, and we used to check whether there exists a bijection or not. Okay, and we had seen that there exists how to construct a bijection. For example, interval 0 to 1 and 0 to 2, if we take, I know f of x is equals to some 2x will work. Okay, and we had checked that there exists a bijection. So on similar grounds, what we have to take, one set should be a set of natural numbers, and here there should be another any kind of bijections. Okay, so you have to similarly construct a bijection from the given set and a set of natural numbers, and you have to see check whether it's a bijection, and you have to see that it's a countable set. Okay, and if you can't construct bijection, that means it is uncountable.